This morning, I gave a presentation about how to get started with resilient software design. So some very simple pattern that you can start using immediately to improve your system design without having to learn a lot of magic or anything like that. This talk will be a little bit different. Here, I will talk about the challenges and pitfalls you might experience if you want to establish, if you want to start using and implementing resilient software design in your company, in your project, wherever. And so most of these problems, issues, challenges will not be so much technology related, more different things that get into your way. So if you need a really hardcore tech session right now and say, yo, well, I need some code. I mean, otherwise I'm going to whatever. Then probably this is not the perfect session for you. Otherwise, yeah, let's try to have an interesting session in the next 40-45 minutes. My name is Uwe Friedrichsen. I work at a company called Codecentric, and on the internet, you usually find me with my handle ufried, so on Twitter or on Speaker Deck, where you can download the slides. I missed that in the morning, so I also uploaded my slides to the JCON site, so you can also download them from there. And there's also a little blog that I write, ufried.com. But that's enough about that. Let's get started. So let's say you want to do resilient software design. You heard my session in the morning, you heard something else, you read something about it, whatever, you attended a workshop, blah, 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 whatever. You say, yeah, that's it. And it's so obvious we need that. I want to do that. And you go back to your company and you want to start that. And then you're completely convinced it will be more like a breeze. So everything going smoothly, like sitting on the beach with a cocktail in your hand, nice, cool breeze, smooth music in the background, everything, because it's so obvious we need that. And suddenly you realize, oops, this feels a bit different, or even like that. And you still stand there with your cocktail in the hand, shivering, and ask yourself, what the heck went wrong? These four letters are heck, of course. No, it's not that you get any wrong impression. So what went wrong? And of course, there are a lot of things that can go wrong in this way, but there's a good chance that you fell more or less prey for some of the typical pitfalls and on this way to resilient software design. And what I'm going to do in this session is I will talk about a few of them. So I collected 7 of these challenges or pitfalls. I called them quests. It sounds better, of course, so a little bit more adventurous. But yeah, it's these things that you need to overcome to be successful, besides knowing the technology. Okay, let's start with the first one. Quest number 1. Understand the business case. If you don't understand the business case, all your attempts might get stopped before you even started. That's a bad thing. So let's talk a little bit about the business case. So let's say you come back to your company and you ask your manager or tell your manager, we need to do more resilient software design. And then she or he might ask you counter question. Oh, okay, cool thing. How much money will we earn with that? And they ask for the business case for the money you earn so the money you get from your investments. And which is a valid question because I mean, as a normal company, you need to make more money than you spend. So it's often a good idea to ask, how much money will I get from my investments? Because otherwise salaries don't get paid and all the nasty stuff are going to happen. And no one of us wants that. So it's a reasonable question. it's just complicated if you don't have an answer. And you also have the same situation, for instance, in your project context. If you go to your product owner and say, yeah, let's do more resilience, let's build more resilience, and she or he will ask you, oh, does it improve our velocity? Which basically is the same question. So do we make more money by introducing resilient software design? So reducing our efforts and all these things. And yeah, well, again, it's a valid question, but if you don't have a good answer, you might have a problem. And here's the key point about the business case. Resilience is not about making money. It's about not losing money. So it's a little bit like security and all other things. If you get it wrong, you might lose a lot of money. So the business case, the calculation is a bit differently than in normal situations where you say you do something and you earn money with that. So here the reasoning is a bit more like, okay, if you lack resilient software design, you end up with a reduced system availability. That's happening because of some non-deterministic effects of distributed systems. I will talk about that in the second quest. And if systems not available, users cannot do what they intend to do. So one of the consequences is in that time period, you can't do anything. So you get less transactions per time period, which is immediate lost revenue. So let's assume you have an e-commerce site. They can't buy anything from you while the system's down. You lose money. And most systems, you lose money if they're not available. And the second effect is a delayed one. That's, well, if that happens more frequently, your users, your customers get annoyed and they will go to the competitor because their website works better or their application. And so you lose even more money. That's delayed lost revenue. And basically, that's the resilience budget we talk about. So it's a bit different calculation. I will talk about in the 6 quests how to invest that budget. So bear with me for that one. But looking at that picture, it should be clear, okay, there's a little bit of different discussion that we need to do when we talk about how to implement or how the business case for resilient software design should be. Okay, so much about the business case. I hope I gave you a few ideas. Now the next quest, that's a daunting one, to be honest. That's much worse than the business case. Embrace distributed systems. That's a hard one from all I've seen, because they are quite different. So say distributed systems are hard and most people just nod and say, yeah, but really understanding the consequences. And as Werner Vogels, CTO of Amazon, said, so his definition of distributed system is everything fails all the time. There are a lot of things that can go wrong in distributed systems. And one of the biggest problems here when learning about distributed systems is if we look at what we learned in our IT education or what we need for distributed systems is quite differently, because in our IT education, we learn to reason about deterministic thinking. So if X happens, then Y. If X, then Y. It's what we always do the whole day if we write some code and so on. We have this deterministic thinking. If something happens, then something else needs to be done. So I call that in-process thinking, inside process thinking. So this reasoning about deterministic behavior, it's what we learn in computer science. It's what we learn in our code routines, in our cutters, in everywhere, and designing a deterministic system. And it's important that we know how to do that. And the good thing is that our brain also supports it quite well. So we are quite good at doing that. The problem is distributed systems are a little bit different. So if X, then maybe Y. It can happen, or maybe not, or maybe it's not exactly the same thing. And yeah, we don't know exactly upfront, and there's a little bit of a probability in here that it can go wrong, and all these things. And this maybe that changes everything, basically, because now pure deterministic reasoning doesn't work anymore. So you need to think cross-process boundaries, a cross-process thinking, and non-deterministic behavior. You have to deal with complexity, with probabilities and all that. And we're really bad at that. And almost nothing in our education trains us for that. So most computer science education doesn't tell you anything about that. Most of the trainings we do afterwards, where we learn about new technologies or coding practices and so on, don't tell. So yeah, and therefore, usually we use deterministic thinking to reason about distributed system, but that will go wrong terribly. And to make things worse, even computer product vendors try to always to hide distribution behind nice interfaces. We've seen that with DCE in the 90s, with Cobra in the 90s, with EJBs, with DCOM, with SOA, and with tons of products that say, hey, here's a nice interface, and it looks like a local processor, like a local call. It just gives you a nice little I/O exception, and that's it. But these two things are fundamentally different. This non-deterministic behavior gives you lots of effects that will blow everything up that you're used to, basically. So bottom line here is embracing distributed systems. You need to understand that distributed systems are going to introduce some non-deterministic behavior. So regarding completion of execution completeness or message ordering, communication timing, all that. And that also understanding that your infrastructure cannot hide that from you. The infrastructure can support you dealing with these things, but it cannot hide it from you. So you need to deal with these effects at the application level. And so you need to have a plan for that. But first of all, you have to understand what can go wrong. And that's a hard thing. It's a really hard one, actually. I'm dealing with distributed systems for almost 30 years now. And well, they still bend my mind all the time. That's a tough one. So, but maybe spend a little bit of time if you like to go into microservices and so on, because that's distributed systems. And also your system landscape you're working in is distributed systems usually, because all these systems call each other remotely in some way and. So it's worth the time understanding at least a little bit about these effects. But it's a big one. The next one I want to talk about is related to that one, but it's a little bit easier to master. It's about avoiding the 100% available trap. So it's basically an effect of what we just talked about, but it's a bit smaller in range. So give you an example here. For instance, version 1. You see that, of course, you understood it, that something can go wrong. And so due to a remote call, and you go to your product owner or your business owner and say, well, how should that application respond if here this kind of technical failure occurs? And your business owner may respond that, wow, no, that must not happen. It's your responsibility to make sure that this will not happen. So business owner just fell for the 100% available trap, assuming that it can be made sure that everything is available 100% of the time, which is not. So, but it's not only happening with people who are not that familiar with IT. It's also happening, I've seen that quite often in the developer community too. For instance, this is another version which I almost had literally this discussion. I did a review for little service design, and they had then a lot of services, and all these services depended on one central service. And then I simply asked them, okay, and how do you handle the situation if that service here in the middle, that central service, is not available for some reason? And then I got the answer, well, no, didn't do anything because, well, I mean, this central service is so important that we have to make it highly available anyway. And so we do not think it's worth to implement anything else then. So yeah, just fell for the 100% available trap, which is that assuming that they can make this service and the network connections going to that service 100% available all the time, which they can't. And yeah, the other developer then added just, yeah, well, if that service should be down, we would not be able to do anything useful anyway. So it just needs to be up. So, okay, they also told me that they got the service design in a way that they were that they had to blindly rely on the availability of their service. So they even got the functional design wrong in some way, that it didn't support here distribution in any way. We will talk about that in the 5th challenge a little bit more. So yeah, so 100% available trap, assuming that everything, you and everything around you is available 100% of the time. But as I said upfront, that's not possible. Availability is always a number less than 1 or lower than 100%. And so, well, the question is not if a failure will happen. It will. It inevitably will. But the only question is when it will happen. And usually it happens at the best day of your year, when you make most revenue. Then the failure will happen. And if you don't take any precautions, don't implement any countermeasures, well, it will happen you badly. It will hit you badly then. Okay. Just a little example here. That's what Google did. They had the Chubby, that's a distributed log service, an internal service they're using in many places. And what they realized is Chubby was a quite reliable service. And they realized, wow, if Chubby goes down for some reason, a lot of other services are also going down. Maybe they blindly rely on the availability of the service, or this 100% availability trap. And what they did, that was a quite interesting thing. They didn't make Chubby more reliable and higher available as most enterprises would usually do. They said, well, maybe it's a better idea to introduce regular outages into Chubby to make sure that nobody is blindly relying on that. And they did it. And so all the other developers knew, oh, well, we cannot rely blindly on Chubby, so it can be down, and it improved overall availability a lot. Just as an idea. Okay. As I said, 100% availability trap, a bit easier to master than the understanding distributed systems as a whole. But let's move to a different ground with quest number 4. It's more on the process and organization level. We need to establish the ops dev feedback loop. And I deliberately wrote ops dev, because if I would have written DevOps, everybody would have made up their mind immediately before I would have said anything about it, because DevOps, everybody has an idea what DevOps is. Unfortunately, no two ideas are the same. It's quite a blurry term like agile or anything like that these days. Okay, so the ops dev feedback loop. And the problem is about the big wall between dev and ops that we still see in many organizations. So it often is that there are just tiny holes poked into that wall, which describe the official paths of your software development process. Okay, if in this period of the process, you may throw something over the wall and blah, blah, blah. And here's a ticket that may come back and so, but no other communication. All other communication needs to go up the line of command. So all the organizational ladder up, usually up to the C-level, so the CIO, which is the first person that sees both sides, dev and ops. And you cannot establish any feedback loops between dev and ops on this communication path, basically. The whole organization idea that's rooted in industrial production, division of labor to optimize cost efficiency and productivity. So how much can I produce with how little money? And which is a valid idea in some contexts if you really go for cost efficiency. But in terms of feedback processes, it's a quite bad idea. Because I already mentioned that before. In a distributed environment, it's not possible that you solve all the availability issues simply at the infrastructure level so that ops alone can take care about that. Many of them will hit you at the application level. Maybe your infrastructure can do a retry for you if something goes wrong, but if the retry goes wrong, you have to decide what to do. Or you can get a request or a response that has wrong values that you cannot process. The infrastructure cannot figure that out for you. So infrastructure can give you some generic support, but at the end, you have to respond to the things on the application level. And so at the application level, you start then to implement some of these things that you're saying, I think that's a good idea to implement that. But you only know if it's really a good idea if you see how it works in production. And so you need this feedback cycle. So you start over there and say, yeah, I implement some resilience measure over here, and then I ship it to production. And in production, it runs, and you get figures for monitoring and so on. And you will see, and then you get the figures back and see, it worked that way. Well, it wasn't exactly what I expected, so let's change a little bit. Here, that's how it's working well now. And now it's good. And now let's move on to the next one, and so on. So it's this build, measure, learn cycle that you have, a full feedback cycle that you need to continuously improve your resilient software design. Now, if you build up this wall, then this cycle is broken, interrupted. I mean, you sit over here and know how to implement these measures, and you have access to the application code, and operations side has access to infrastructure and monitoring. So, well, it's broken. And the worst thing that I've seen is in there that on the development side, you're shooting at the dark, and shooting at the dark is really discouraging over time. So, I mean, you're guessing, you're doing guesswork, and you don't get any feedback. Is it good? Is it bad? And so you stop doing it. So it doesn't work. Overall, you need to have this feedback loop from ops to dev, from dev to ops. Continuous feedback loop. Both parties need to have fluent conversations for really getting resilience, robustness, availability right in your system designs. And there are a lot of things how you can establish these feedback loops. For instance, you can go DevOps, the original idea of DevOps. So accelerating the way through the IT value chain. So how fast can I take a business idea and implement it in our code, ship it out to our users, and collect feedback from them to learn on the business level from them. And this has all time, so this triggers all sorts of feedback loop to get it shorter and shorter. And this also results in a good feedback loop between dev and ops. But it's always business and dev and sec and QA and ops. So if you talk about biz DevOps, it's DevOps. If you talk about DevSecOps, it's DevOps, and so on, at least if you go back to the original idea. But for some companies, DevOps is a bit too big, so they just implement some DevOps team, which is, well, usually nonsense. So a team that communicates between dev and ops is allowed to jump across the wall forth and back. Well, which is not DevOps and doesn't help too much usually. Or maybe you don't want to go with all these process and organization changes that it triggers, also DevOps. And so you say, I want to have something smaller, maybe site reliability engineering from something that Google invented. And they had the problem that they had to balance feature development speed and production stability, exactly the issue that we have here, that we deal with here. And so they came up with a nice concept how to make sure that they balance capacity in some way, that if the production stability goes down, that you implement less features and fix or care more about production stability. And if production stability is fine, that you have more time for implementing features and so on. So nice idea. Some books available about that. Or maybe you have your own way. But however you're doing it, make sure that you get these feedback loops in place, because otherwise it won't work. Okay, so much about feedback loops. Now for another daunting topic, more on the design side. I already mentioned that briefly in that when I gave you this example for the 100% available tab. We need to master functional design. And that's also a hard one. I rarely see it done right. And why is that the problem? The problem is, without proper functional design, all the other measures will not help. You can implement a million circuit breakers and back pressures and timeouts and whatever you want to implement. If you screw up your functional design, it doesn't matter. So let's dive a little bit deeper into that, what I mean with that. Let's talk about isolation for a second. So isolation is a core principle of fault-tolerant software design. Fault-tolerant software design is, let's say, sort of a prerequisite of a foundation for resilient software design. Without robustness and fault tolerance, you never will go and be able to implement some kind of resilience into your applications. So it's sort of a prerequisite. And one of the core concepts here is isolation. It says, well, your system as a whole must not fail. That's important. And to achieve that goal, you split up your systems in several parts and you isolate them against cascading failures. So if one part of the system goes down, it does not affect the other parts of the system. And that is isolation, basically. It's the basis of fault-tolerant software design and also a foundation of resilient software design. So, and to do that, you implement then these parts, call them failure units or units of mitigation. And these functional slices, then you isolate them via bulkheads, so making sure that these errors do not spread around. And on the technical level, you have a lot of choices like services, micro or not. You may have actors or communicating sequential processes, so coroutines or self-contained systems, or whatever. And yeah, that's not the hard one. The hard one is the functional level. So deciding which part of your functionality goes where, into which of these failure units. And that's pure functional design issue, and it's extremely hard. Now you might say, well, no, that doesn't sound hard. I mean, we dice and slice functionality all day. We slice them and between methods and between classes and modules and services and all these things. And say, well, yeah, it's true. We're doing it all day, but how can we avoid this situation? We have a service A, gets a request, an external request. It tries to answer or wants to answer. And for answering that request, it needs to reach out to service B and ask that service for some information or whatever, and in order to complete that request, the external request. But if service B is down, and so the problem is then service A cannot answer the external request without getting the response from service B. And if service B is down, service A is down. So we have broken isolation in that scenario. Bad thing. But we don't want to have that. But looks familiar, doesn't it? I mean, that was the situation that we had in that example I discussed before with the central service. That central service that was service B, basically, and all other services were service A, and they needed to access service B. And if service B is down, they didn't work. Or how do we avoid this situation? So, well, we may write a service and figure out, oh, whoa, that's a big one. That's a big one. That's not a microservice, it's a humongous service or something like that. So let's better split that up and split it up so into some other service. Oh, it's still quite big. So let's split them up a little bit more. And now we've got microservice that fit in our heads. So now, which is okay. The problem is now to answer the external request, you have to reach out to a lot of internal services. And if any of them is down, you cannot do your work. And additionally, so availability will hit you. issues will hit you. And also you build up a lot of latency because calling all these services takes time. And so your availability is again broken by design. And by trying to fix that, you put the logic together a little bit more. And well, in the worst case, you end up with some kind of mothership service where everything's in, which breaks isolation by definition, because, well, isolation says split up the whole application in several parts, and you just didn't. Bad. But you don't give up that easily, which is good. Yeah, come on, we know our trade. We know how to do things. So let's throw our well-known best practices at that. So divide and conquer, so functional decomposition. We learned that in computer science 101. We know how to do that. Or we went to a lot of clean code sessions and code retreats, and they always told us, dry, don't repeat yourself. Or if you're more into software architect level, you say, yeah, we design for reusability. It's the holy grail. It's reusable. It's important because it increases our productivity and so on. I'm allowed to say that because I work as an architect quite often. So to make fun about architects, because I'm an architect myself. Or layered architecture, the other holy grail of software architecture. Show me your architecture, layer 1, layer 2, layer 3, and because it doesn't work, here's another layer which lies upside down, something like that, and so on. And some people come along and say, we don't do anything like that. We are just going to do TDD for figuring out our design. And there's nothing wrong with TDD, using that. But don't think that anything will change magically in some way, because what you implicitly do if you do all these refactoring is you apply all these tactics that you've learned before. So you will apply your don't repeat yourself, or your functional decomposition, or your layering, and all these ideas. Unfortunately, this is reusability or dry. Because service B is the reusable part that you can reuse, and service A is trying to reuse that part. And if service B is down, service A does not work. Usability is one of the tightest forms of coupling that you can imagine. And this, of course, is functional decomposition and layered design. And if you look at that quite clearly, you will realize that I ended up with quite high coupling between the services, but low cohesion, which is quite the opposite of what you try to achieve. And so you try to fix the cohesion part, and well, you're back here. Welcome to distributed hell. So just to be clear, all these design practices I just talked about are great ideas inside a process boundary. They work very well in most places there. Across process boundaries, they do not work well, because of this non-deterministic behavior of remote communication distribution. Some people then come and say, well, but we can use caches. Caches are not the worst idea. So like saying, okay, here in service A, we have a cache in here and we can't reach service B, then we use the cache value and everything will be fine. And again, that's a reasonable idea in some places, but if you use that all over the place to fix bad design, you end up in a different situation, which I tend to describe like, do you really think that copying stale data all over your system is a suitable measure to fix an inherently broken design? So caches cost resources, caches cost energy, caches cost network bandwidth, which can be a problem if you use too many of them. And caches have out of sync data, so these outdated entries, stale data that you also have to deal with. So be careful. It's not a fix all. It's in some places can be used, but not. So bottom line, basically we have to relearn design for distributed systems. And yeah, well, it's not easy. Sorry about that. I did a talk once, getting service design right, with sketches a few ideas. You find some ideas in the domain-driven design community, not in the blue book, to be clear. It's some other ideas around there. there are some ideas around here, but basically we haven't solved that problem very well up to now. Now that was a daunting one again. So number 6 is more about the patterns themselves. So let's assume we got the service design right, and now we want to augment our service design or implement here our whole design implementation with some resilience patterns. And here it's about knowing your toolbox. First one is knowing what's around, what's available, and that's quite a lot. I mean, I use this image in some of my workshops, and it's just some of the patterns that exist. There's a lot more in place. There's also a lot of anti-patterns that you should know and so on. But more important than knowing what's all there is how to use that, because it's quite tempting to, yeah, oh, that's interesting, let's use all of them. And that's a very bad idea. I mean, it's tempting to try them all out, but it's a bad idea. So here's the challenge that you have to master. First, understand patterns are options, not obligations. You can use them. You do not have to use them. So try not to pick too many patterns. Try to get along with a few ones, because each pattern increases the complexity of your code. And harder to read code is harder to maintain. More errors will slip in and bugs slip in and so on. And so in the end, your code will become more brittle instead of more resilient if you do too many patterns. So there's a sweet spot somewhere between doing nothing and doing too much. And if you do too much, you increase your complexity, and complexity is the enemy of robustness. And you need robustness to implement resilience. So additionally, each pattern costs money in development and ops. You have to implement that, you have to maintain that code. And usually you need to extra hardware, infrastructure, and so on to run that stuff, especially if you use redundancy, which you will use quite often usually. And you only have a limited resilience budget. We talked about that in the first quest. So idea is try to look for complementing patterns. Here's, just to give you a few examples, here's how other people did it. So if we look at Erlang, and Akka is the Java or Scala implementation of Erlang runtime, basically with a few changes in there. So what they did is they used an actor model as failure units and messaging as a communication paradigm. And then they implemented this let it crash pattern, which is a combination of some monitoring, some escalation techniques, so worker supervisor chains, and restart logic. So if the worker crashes, the supervisor restarts it. And they have some heart beating implemented to figure out if some other remote Erlang virtual machine is still online. And finally, the Erlang virtual machine supports hot deployments, so you do not need to restart the application to get a new version running, which is basically all they had. And with that, they were able to implement some telephone switches, communication switches, with an availability of 9 nines, so 99 point and then 79%, which means that over 20 years, they accumulated about, I think, half a second of downtime roughly, which is impressive, just with these few patterns. And Netflix, around 2015, 2016, so when they were quite popular and their Netflix OS were quite popular and so on, they used some service design, microservices, we called them later on, and HTTP-based communication, so request response. And because it's a request response, they put a big effort into managing latency. So they created the Hystrix library, which has a combination of timeout, circuit breaker, of retry logic, of going for bounded queues and implementing fallback logic and all that. They also used redundancy in many places, so auto-scaling, share load. They have very sophisticated monitoring for their system landscape to figure out if something goes wrong. And they do not have hot deployments because they rely a lot on the JVM, and JVM doesn't support hot deployments out of the box. So they use canary releases for still going for zero downtime deployments. And finally, they have the Simian army for error injection to figure out if their code is really as good as they think it is. And it's a bit more, it's a different business case also, but it's still quite Nice. Basically, not that many patterns, and it's very impressive what they achieve with these few patterns. So look for complementing patterns. Don't try to implement too many patterns. Okay, let's finish up with the last quest number 7. That's one that's not specific to resilient software design, but which is a problem that we have all over IT, basically, but which also hits us in resilient software design. That's how can we preserve our collective memory? So my observation of the years is we lose our collective memory every 5 years. So as a community, that's when most of the discussions start again in the community, start over from scratch, as if all the prior discussions never took place. I once attended very good, really good unconference with very engaged people. So it's really great thing. And there was a session about reusability. I said, well, that's interesting. Let's listen to it. Let's listen what other people think about reusability. And it was a devastating experience. They started discussing really eager, really into it, and as if nobody would ever had said anything about reusability. Nothing about what we know from the 60s, from the 70s, from the 80s, from the 90s, from the 2000s, from the early 2010 was 2018, 2019, just before COVID was, and nothing, as if it was a completely new topic. And I mean, everything we need to know about reusability is known. It's known since the early 70s, and not there. And I asked myself, wow, why is it that way? And I have 2 parts of an explanation. The first part is basically say, well, while we're working in our professional life, we learn things. So hopefully we learn things all the time. Not true for everyone, but well, let's assume we learn and learn and learn and learn. We build more knowledge. Knowledge can be good, knowledge can be bad. You can learn good things and bad things. And then over time you build insights. So you learn how to separate the wheat from the chaff. Basically say, okay, oh, that's a timeless knowledge. That's timeless wisdom. And that's just, yeah, well, I can use that now, and that better forget about that over there, and so on. That's insights. That's a different thing. And you need a lot of time to build insights. So it's builds a lot slower than you build knowledge. And in IT, basically we have, I heard a number that every 5 years, we double the amount of people that work in IT, which means that, 50% of our people in the community have less than 5 years experience. Well, and that's a time where you build knowledge, but not that much of insights, usually for yourself. And other domains also have these types of problems, maybe not that extreme, but also these types of problems. And then, the question, what they do then is, well, they try to preserve these insights and build some kind of body of knowledge and so on. So engineering practices. And what do we do? Well, we do it a little bit differently. We say, well, is there anything new at the horizon we can use to solve this problem right now? Because all stuff, that's useless crap. So we have a cult of new. So everything new is cool, is shiny, and so on. And if you come along and say, well, here's an idea from the early 70s that can help you to solve that problem, everybody comes back, then you will say, well, okay, take your walk and go back to your retirement home. We are looking for this cool new library over there, which will solve our problems magically, or something like that. I mean, it's not always this harsh, the conversation, but we have a habit to always go for the new stuff and discard all the old stuff. And there's, to be frank, there's old knowledge we better discard, but we also discard all the wisdom that we achieved over time, the insights, and that's a problem. So, and therefore we have to rediscover our insights basically every 5 years from scratch, or how I like to phrase it, in IT we suffer from continuous collective amnesia, and we're even proud of it because, hey, we're so innovative. We always do only the new and shiny stuff, nothing of this old. And the question that I have is then, how can we become better in this area? I mean, it also affects us in resilient software design, because fault tolerance, resilience, and all these ideas, they are not new. They are decades old. We just forget about them over and over again. Therefore, it's our seventh quest. To be honest, I don't have a clear answer how to solve that. If you have an answer, please share it with the community. Maybe we figure out how to become better with that. Okay. These were the 7 quests. Let's wrap up so that we have time for a few questions then. These were the 7 quests I talked about, from the business case to preserving our collective memory. And if I look at them, maybe I would like to add a few closing thoughts. We've seen road to resilient software design is not that simple. There are some obstacles in the way that probably we didn't think about when we start our journey. And most of these challenges are only indirectly related to resilient software design, and not even coding related in some way. Okay, that's so a lot about processes, mindset, and so on. And especially in our domain, mastering functional design is very hard. That's what I've learned, because there's few materials about that, how to do functional design good in distributed environments. The pattern itself are relatively easy. It's also hard to get your head wrapped around the distributed systems and or changing the organization. Okay, we all know how hard that is. So it's not easy to get it done, but we need to do it if we really want to have resilient applications which run reliably in high availability in our production. And the last question, of course, is how can we preserve our collective memory? It really have no idea, but we need to become better to master that one. Okay, that's what I had for you. So thanks a lot for time and attention. I will stop screen sharing now and have a look into the chat if there are any questions. Do we have a good counter argument for the statement we will deal with resilience issue when they occur? Oh, that's an excellent question. I'm not sure if I have a good one, but the thing that I tend to say in a polite way is we can either, so things will go wrong, guaranteed. So there's no question if they will go wrong, they will go wrong. And usually they go wrong if there's really high pressure on the system. We can either discuss what we want to do now or then. What probably some high-level manager then will run around and ask whom they can kill because who's guilty of these things and so on, which is not that nice situation to discuss that. So maybe it's a better idea to discuss that now. Doesn't always work, but at least it's worth a try. But when you split up your business to smaller bounded contexts, you can implement instead of dry microservice hell. So instead of a higher, yeah, absolutely, absolutely. So I'm a big fan of microlith or modulith and however you call it. So if you have use cases, use case design, so use case oriented design, so going along with user interactions or use cases instead of functions or entities and anything like that. Absolutely, and also modulates can often do the trick, but you have to make sure that you do not mess with the module boundaries then. 3 or 5 years collective memory page. Was it Uncle Bob who said that all 5 years are double? So yeah, I think he said that in one talk. Yeah, absolutely. Right. So I have the whole story of a page. Also, yeah, multiple versions. Okay, that's or now we're back to Uncle Bob. All right then. Okay. Are there any other questions? So maybe we can go for one more question, then better unmute yourself then if you have one more. No other questions for now. Okay, then thanks a lot for your time, for your attention, and good luck.
There's one more question where the slides are available. Sorry to interrupt you.
Great. No, that's perfectly fine. Yeah, slides are, I've uploaded the slides to the jconscat.com here, to the website, and you can also download it from my speaker deck. So speakerdeck.com/ufried, that's also available over there. So you can download the slides on both places.